Hello everyone, I am Abhishek Naik. I am a PhD student here at the University of Alberta, computing science. Not for long though, my defense is next month. And yeah, so here is something I want to tell you about. And I also wanted to, I guess, say something which is maybe not said that often in research talk is that, things don't work. Sometimes you fail, right? And so I'm going to touch upon that a little bit in this talk because, yeah, this wasn't the easiest project to do. In fact, yeah, I guess in a way, this is the hardest thing that I've ever done, right? Because this is theory, and I am not a theoretician in any sense of the word. I had no other theory training before I came here, or even when I got here. And so then you might ask, okay, how did I even end up doing theory? So that's a good question. So this was so story time. This is sometime mid 2021. I am back in India. It's COVID time. Canada has stopped all flights from India to Canada, so I'm stuck there. But I'm working there. All we need as CA students is a laptop, right? But I was staying in a humid place, actually a coastal city right next to a beach in Goa. If for the people who know, it turns out the humidity was a little too much. My laptop stopped working because a lot of humidity got inside, and it just screwed up the logic board, right? So okay. The only thing that I could use for my research, I no longer have access to it, and so I panicked. And I went to a Apple repair store. They kept it for 3 days and quoted me like a $1,100 bill to replace the entire thing. I wouldn't get any of my data back, and I was losing a bunch of code that I've written in the recent past. Please git push your code at the end of every day. Don't make mistakes I did. But anyway, so I emailed it that, hey, there is a problem. I don't have a laptop, and that's how I do all my research. And I can't come back to Canada yet. It's going to be a while. What do I do? Do I get it repaired and resume work in like a week or something? And Rich was like, okay, it's a $1,100 reply. The new laptop is like $1,300. Might as well get the new one. I was like, old laptop with none of my data, new laptop with none of my data. M1. So, okay. But then I have to wait for like 3 weeks or so to get it, right? Because I have to get it here. And so it said, okay, why don't you do some theory? That's interesting. But then the thing is, just before I got home, we had published this paper, and this was about a bunch of learning and planning methods in the average board formulation. And this was a work with he, and he is amazing. Like he is as good a theoretician as it gets. And so there are a bunch of algorithms in this paper, and we had all come up with those algorithms, and he had done all the convergence analysis, all the hardcore stuff, and I had done all the experiments, right? And we wrote this nice paper together, and I was very happy with it, right? Like using the best of our strengths, we got us something which is better than what each of us could have done individually, right? That's what collaboration is about. Great. But then it was also like when I thought about what Rich was saying to do some research, I was like, yeah, maybe that makes a little sense, right? Like, in a way, I did feel bad that I had to ask someone to do the theory because I couldn't, right? Not that I wanted to have the choice to say, okay, I can do it, but I choose not to do it because, I don't mean it in a bad way. I just meant that if I like something more, and I have limited time, then I should do that, right? And so I'm like, okay, I need to have that choice. That means I have to, maybe I can learn a little bit of it, right? And okay, one of the most obvious future works of this project was that this is not one-step methods. That maybe I can show you something. So these are one-step methods in which you learn you have all of these are online algorithms. You're interacting with the world, you're getting some data, and every time you get some new data, you make some updates, throw that example away, and then keep doing this over time, right? And so every time you're doing things which are very local with information which is very local, and it works out pretty well, right? So what we want is more efficient credit assignment methods. And what usually happens is, let's say this is a grid world, your agent is starting from that corner. It doesn't know anything about this world, right? So it just goes around randomly and maybe it hits some goal location and gets like a +1 reward, right? So what a one-step method would do is that it would update the values just before the goal, right? Because that's where it saw something which is non-zero, right? A positive reward, and it will make an update towards it. And so you can think of it in the learn policy or the values. But what a multi-step update can do is, after seeing that one example of hitting the goal, it can make these updates throughout the trajectory, right? Like it sort of has a memory of how the agent has reached this place, and then it tells all of them that, okay, you were responsible to this extent to the reward that we got, right? And because this was nearer to when the reward was, you got the reward, this is a bigger update compared to, this thing fading over time. Okay, all of this makes sense, and we should have this, right? This is a no-brainer, right? If we can do this, we should try. And so that is what I wanted to do. And I decided, okay, I'm going to develop the multi-step methods, and I'm going to work out the theory myself, right? I don't have to start completely from scratch because there is already some theory, the one-step theory, right? And now I have to sort of probably generalize it in some way, and I have no idea how, but it should be possible. Okay. 2.5 years later, okay, so before I tell you what it is all about, I need to tell you what I'm trying to do, right? So all of these methods are within the average reward formulation, which is within the a framework of some agent interacting with the world. It observes some states of the world, take some actions, observe some corresponding rewards, and this goes on forever. So there's a setting in which the agent environment interaction goes on forever, and then you get a stream of experience like this, right? Some S0, action A0, reward R1, and so on and so forth. And what you want to do is, let's say you are behaving in a certain way. You have a policy that given some state, I'm going to act in a particular way. Now you want to evaluate whether this is a good way to act or not, right? So you want to evaluate how good this policy is, and how do you evaluate in terms of the rewards that you're seeing. So these are the rewards that you're seeing, and you can say, okay, if I denote the policy with which I'm behaving, the average reward for that is just this complicated looking thing, but it's quite simple. It's just the sum of rewards divided by the number of rewards, right? And you're taking the expectation to remove the noise from the observations that you're seeing, and the limit tends to infinity because you want to see this reward over for a long time, right? Okay, and then so this is one way to evaluate a policy, but you can also evaluate how well you're doing in every state that you're in, right? So you can say my value at every state when I follow policy phi is starting from some in that state S. What is the sum of rewards that I get after I've subtracted the average reward from each of the rewards, right? So what this gives you is, starting from this state, how much more reward do I get than on average, right? This is encoding, this value function. And just to contrast it with something that you probably are more familiar with, in the discounted formulation, the future expected value of a state is, sum of rewards discounted by a factor which is within 0 and 1. But so all you're doing is removing that gamma and then subtracting the average reward alpha, right? Okay, so now the prediction problem is to say that estimate your average reward and the value of every state corresponding to that policy using data generated by some arbitrary policy, right? So you're not following this, you may not be following the same policy to generate the data which you want to evaluate. Okay, so that's the prediction problem. And okay, so the on policy setting is where you behave in the way for which you want to evaluate, right? So if I behave according to the same policy pi and I will evaluate the same policy. So this is like the simpler setting, right? What we are going to do is we are going to estimate the value of a state as a linear combination of the some weight parameters, right? So you'll have some features that you see of the state encoded by some xs, and then a W transpose x of s will give you the estimated value of that state. Okay, now the one-step method that I was talking about earlier make updates like this, right? So they will update the value, the weight parameters. The old ones are the new ones plus, maybe I can use a mouse. Yeah, okay. New parameters are old parameters plus some step size times the TD error times the feature vector, right? Where the TD error is the reward that you saw in this transition minus your current estimate of the average reward plus value of next state. There should be a minus here, minus value of the current state. And these one-step differential methods update the average reward by doing something very similar. Now your step size is scaled by some eta, but you're still using the TD error as well. Okay, so we can talk about why this is special in this way later. But let's just say, okay, this is established theory. In that paper, we showed that if you do this under some technical conditions, this is guaranteed to converge, right? Great. Okay, so now we want to make the multi-step version of this. Now that is fairly straightforward, and I've highlighted the difference with this sort of blue box, right? So everything else is the same. Now instead of this feature vector here, we have this eligibility trace vector, which is this memory thing that I was talking about earlier. The TD error is the same, and now your trace evolves in this way that you decay it with time and add the new thing that you just saw, right? So this gives you that effect of diminishing updates for things that happened quite far in the past. Okay, so this is like an obvious generalization from that one step to the multi-step case. Let's call it algorithm 1. Is it guaranteed to converge, right? Now, the first part is easy for me. Like I have good intuitions to come up with what seem to be reasonable algorithms, right? And maybe I can say something about, oh, the fixed point, like if you run this algorithm for a long time, maybe this is where it will go. Now, can I actually show it? That is not what I ever had any training, right? But so that is what I wanted to do. I wanted to get out of my comfort zone and figure it out. But yeah, it's quite complicated, right? And when I usually sit in a theory talk, I maybe understand the first 10 minutes, right? I see a lot of nods. I'm not alone. Good to know. And this is supposed to be a theory talk, but I'm going to try to make it. I'm going to try to give you the intuitions for why things are working in a particular way, right? And then show you how I used it. So let me try to give you some intuitions about convergence theory. Okay, so what I'm going to analyze are these sample-based RL algorithms. Lab.
What are you trying to converge to?
Sorry?
What are you checking the convergence to do? Like what are things converging to here?
Okay, so that is asking what are things converging to here. So so the answer depends on the particular setting you are in, right? So if you're in the tabular setting, it will converge to the exact differential values or the exact discounted values, which your formulation you're following. If you're doing some sort of linear function approximation, it will converge to like the TD fixed point, which will be, involve some projection operators of the Bellman projection operator and so on. So depending on the scenario, you will have a different point of convergence. Let me put it this way, there might be a different desirable point that you might want to get to. And now the question is, how close do you get to it, if at all? Right, so that's the hand-wavy version of what convergence would mean. I will sort of say what, for the algorithms that I'll talk about, I'll say exactly what it is. Okay, so sample-based RL algorithms is, so what I mean by that is, you're seeing some samples from the world, which is like the transitions of data that you see, and you're making some updates online and incrementally, right? Okay, so now this is like the update tool for like linear discounted TD. right? Again, I tried to put up something which might be more familiar than, let's say, the average load stuff I'm talking, right? So the weights are updated according to the old weights plus some step size times the feature vector, and this is the TDR. Okay? Now, yeah, just a reminder, I'm using like a linear function approximation, right? And so in the tabular case, it would look like this, right? Okay, so now I'm going to take this x of t inside the brackets. Okay, inside the brackets, and I just rearrange these terms. Not super important, but what I want to get with that is now you can express this update into this sort of simpler form where your weights are updated with some with a vector and a matrix A. Okay, and they are both dependent on time because they use all of these things. Now what I can do is I can take this WT on the left side. So what this encodes is a change in the weights is this. Now I can divide it by t plus 1 minus t, which is just 1. So what I have gotten is dWt by dt is proportional to this dt plus at times wt, right? So this is like a derivative of the weight vector with respect to time, and it depends on the weight vector, the current weight vector, and two other things that depend on time. Okay, so this is I guess an equation. It involves some derivatives, so differential equation. It only involves derivatives of one quantity, right, which is Wt. So this is an ordinary differential equation. And yeah, so this is, this is familiar to us, right? Like we have seen this in an undergrad physics course. How? Okay, let's say it's Valentine's week, right? Maybe you and your partner decide, okay, we are going to do a romantic getaway in a hot air balloon. Okay, so you go up there, you see the beautiful city, underneath it's a nice sunny day, and then you take out your phone to take a selfie, right? Because duh, you have to post it on Instagram, otherwise did you even do it? So you take out your phone, and unfortunately the phone drops. There's a gust of wind. So you are in shock. But for the physicist, this is a physics problem. And we can say, what is the velocity of the phone which is dropping from the sky? So let's say this blue dot is your phone. What are the forces acting on this phone? Gravity, so mass times the gravitational constant g. And there is some air resistance, right? We don't live in a vacuum, thankfully. And this, so it will act upwards and it is proportional to the velocity. The larger the velocity, the more air resistance it has, right? So let's say it is encoded by some coefficient of drag, mu times v. And okay, now we can figure out what the velocity of this ball is over time, right? Thanks to Newton's second law. Right? And so the forces on one side, we are taking down is the direction of movement, so mg minus mu of vt is m of at. Now acceleration over time is just derivative of velocity over time, right? So okay, and now I'm going to rearrange this, divide by m, I get this thing. Okay, now g is roughly around 10, and I can pick some arbitrary values of mu and m and say, okay, it's an equation of, maybe this is one of the forms of this equation. Okay, now we saw something familiar before, right? So, some derivative on this side, some constant minus, okay, I guess there was a plus sign there, but yeah, so, okay, so this is something familiar. Now, how does this behave, right? So we can plot what is called a field diagram or something that on x-axis is the time, on y-axis is like the v of t, the velocity of the object. Now, can you tell me for what velocity would there be no change in velocity? So that means at what velocity is the derivative 0? 50, right? So if I plot this out, like if I start at 50, I will stay at 50. There will be no change, right? Because my derivative is 0. So let me, because this is like over time, so let me show this with arrows. Okay. But what if the velocity was, 0, like I'm taking a selfie, it's not moving too much. Now if I substitute 0 there, my rate of change of velocity is 10. So some positive number. So at 0, I will have something that it will increase in that direction, right? And then let's say it becomes, 1 meter per second. You put that in, you will get another positive number, 9.8. But it's slightly lower than 10. So you get another movement which is slightly lesser than that. And then you keep doing that, and you'll see that it eventually converges to this velocity of 50, right? Which is sort of the terminal velocity in the physics parlance. But you can also do something else, right? You can say, oh, maybe I was moving my hand and the phone started with some initial velocity, right? So let's say, what will be the derivative when your initial velocity was, let's say, 100? It will be minus 10, so pointing downwards, right? And then you can also keep plotting it over time, and you'll see it also converges to this equilibrium point, shall we say, of 50. And then you can do this for many other starting points, and you'll see that, okay, all of them start at some place and eventually converge to this equilibrium point of 50. Good. What if we had a differential equation which looked like this? Now there's a plus instead of a minus, right? What will be the, if you start from 0 velocity, there will be some, again, a tangent, 10, right? But let's say your velocity now increases, becomes 1, now it's 10.2, it's even more. And this will keep just increasing, right? Like this doesn't come down to any value. And so for that, the field diagram will look something like this, that you start at 0, there's some 10, you get to, let's say, 10, at 10 is 10 plus 2, 12, even more and even more. So this explodes. So there is divergence for this kind of a differential equation, right? Okay, and in general, things can look quite messy, right? Like I showed an example where there was like one equilibrium point, but here's an example where there are 1, 2, and 3. If you start somewhere here, you'll end up here. If you start somewhere here, you'll end up here. So it's a stable point. If you start here, you will diverge. You start somewhere here, you will converge here. You start somewhere here, you converge. Right? So you can have different kinds of equilibrium points which are stable, unstable. Now, if you want to prove the convergence of an algorithm, there is, you would ideally want it to somewhat look like this, right? That you start anywhere, and then you converge to the point of convergence, right? Like which is like one single point of accordance. Okay, so now the condition for stability for an ordinary differential equation, which looks like this. So we looked at examples where there was like a single variable, right? Like a scalar. And for that, the condition, handy condition was that subtraction term should be negative, right? Like it's a minus of 0.2, then it works. If it was plus 0.2, it didn't. When you have a vector of things, it sort of works the same way, but now you have to say that the eigenvalues of this matrix A should have negative real parts, right? If all the eigenvalues are negative real parts, there is a theorem which says that this ordinary differential equation has a globally stable equilibrium point, W star, such that this is true if and only if A is Hermits. So any matrix which has all its eigenvalues having negative real parts is called a Hermits matrix, right? So if your matrix is Hermits, then the corresponding ordinary differential equation has a globally stable equilibrium point. Great, we could use this, right? Okay, but when we started, simplifying that algorithm, we had something which involved a proportionality sign and two things here that depended on time. And we are here talking about something where there's an equality sign, and these two things do not depend on time. So we still have to go from here to here, right? We have made some progress, but there's still some more to do. Okay, so how do we do that? Okay, again, how do these algorithms actually behave, right? So if you, let's put yourself in the shoes of the agent, like you are the algorithm, you are seeing some state, rewards next state, you make an update, up, down, whatever. Now things are going to be noise, right? Then let's say you start from that initial point here. Because of noise, sometimes you go up, go down, and this will keep moving. So it's not like a nice, straight, smooth line. You start from some other point, you'll see something like this, right? So now one thing we need to show is that wherever, let's say you start the algorithm, the sequence of updates that you make will result in these values which are still bounded. What that means is, you can think of it as like they all always lie in this region. Like they might have a lot of noise, they'll go up and down, but they'll remain in this sort of upper bound and lower bound. Okay. Now the other thing that you need to show that over time, asymptotically, all of this noisy things that are happening, this set of like iterates will converge to the solutions of a ordinary differential equation, right? So these nice smooth things, you want to show that these noisy things over time, yeah, they might have a lot of noise in the beginning, but over time we can average it out and sort of get to this thing. And that is all we need, right? Now we have both of those components, which is that we show that the sequence of iterates is bounded and asymptotically converges to the solutions of an ODE. And then you show the sequence of iterates being like, some W0, W1, whatever the thing. And then you show that the ODE has a globally stable equilibrium point, right? And so that's from the start to beginning, you have shown that I have a sample-based algorithm. It makes updates in this messy way per sample noise. But if both of these two things are true, it will converge to this globally stable equilibrium point, which means it will go there, and once it reaches there, it will stay there, right? That is what we want. Good. Okay, so now we know the basics. Now let's try to apply it back to the algorithm that we started with, right? Which was algorithm 1. Okay, so the updates for the algorithm 1 were like this. There was a trace parameter, and we are updating both the weight values and the average reward estimate with the TD error and the trace parameter, right? Now I can combine both of these updates into one update at the cost of having a messy looking matrix and vector, right? Okay, so it's messy, but at least what we get is a compact notation for this. Now note that again, these two things change with time, right? So now we can do a bunch of linear algebra and show that, okay, in expectation, after a long time, this matrix, this A of t will converge to this A matrix, and it has this form. Okay, the exact form doesn't matter, but what matters is we can show that this is Hermit's. Okay, so that was part 1. We wanted to show that for the algorithms we care about, there is a corresponding AT and BT, and that AT, its expected value over time for that matrix, that's Hermit's. Good, that was one of the steps. The other was to show that the things are bounded and they asymptotically converge to something, right? So yeah, this you can show thanks to some seminal work by Tsitsiklis and Mandroy in 1999, where they did something for what was at that time the first multi-step average reward prediction algorithm, right? So you can use a similar analysis like this to show that this is Hermit's and it's all great. Then you can use another one of their complicated looking theorems, to say the least, to show the other things, right? So look at these two in particular. These are saying something is, the norm of something is bounded, right? Bound, some more bounds here. So basically, if you show all of these conditions are true for your algorithm, and you're shown that your matrix is Hermit's, then basically all of this analysis works, and then you can show that, oh, great, your algorithm converges to the fixed point, right? And to answer Vlad's question, like more formally, this is what the final theorem ends up being, that under assumptions of an irreducible Markov chain, the Robbins-Monroe step size conditions, and the features being linearly independent, this algorithm 1 converges for all lambda and 0 to 1 with probability 1. R bar converges to the unique reward rate of the target policy phi. And the W converges to the unique solution of, yeah, because there's a linear function approximation, some projection operators, blah, blah, blah. And then this sort of tells you what is the quality of the solution compared to the best solution if you were not doing linear function approximation, right? Like if you just had tabular estimates, how well could you do? This sort of tells you that. Anyway, but the harder problem, or perhaps even the more interesting one, is the off-policy problem, right? That you are behaving in some other way, but you want to evaluate something else, right? This is a strictly harder thing to do, and yeah, so that the algorithm that Tsitsikis and Van Roy had come up with, that was a non-policy algorithm, and it cannot be extended to the off-policy case. So basically, that's an unsolved problem. You need to do that, right? Okay, so back to our one-step algorithms. We know how to do this in the one-step case. That is what we showed in the paper that I talked about. And now that algorithm looked like this, right? So I've highlighted the changes from the on-policy case. Basically, the only change is there is an importance sampling ratio in both updates, right? Everything else is the same. The importance sampling ratio is the probability that you took this action according to that policy you want to evaluate, versus how the probability of taking it according to your behavior policy. Okay, so what's the multi-step version of this? So remember, this was algorithm 1. So we need to add importance sampling ratio some place to make this work, right? And the places we can add it are now highlighted in orange again. And remember, the multi-step case is a generalization of the one-step case, right? So if you substitute lambda equal to 0, you should get this back exactly. So I'll let you stare at it for a second while you do that, and convince yourself that lambda equal to 0 indeed gives you the one-step algorithm. Okay. Now, because this is the off-policy version of algorithm 1, let's call it algorithm 1 off. You see where this is going, right? Okay, so now we want to analyze the matrix of A. The A matrix of this 1 off algorithm. Remember that for algorithm 1, the A matrix was this, and we showed that this was Hurwitz thanks to existing work. Now, for this new algorithm, 1 off, it is more complicated. This had a nice set of zeros everywhere. Now there is a non-zero term. And there was all of these d pi's, and now there is a db, which is like the distribution of states that occur under the behavioral policy, right? Okay, so this was what I had to show, that this is Hurwitz, and I could not use this existing result because of these differences. And so, okay, I learned a bit more of linear algebra. I talked to a bunch of people who strictly know a lot more things than I do. And yeah, still many months pass and I could not show that this was Hurwitz, right? And now all of these existential doubts start becoming louder and louder as time passes. Like their function is like this, the diverging. And so after a few months, I was like, oh, maybe it is not Hurwitz. So how do you show something is not true? That's sort of easy, right? Comparatively, you just need one counterexample, and you can say this statement doesn't hold true at all, right? It's much harder to show this is true in every case. So you just have to come up with a counterexample. Now again, this is not my expertise, right? It's like I can just come out of the counterexample. But if you look at these terms, these are all just some matrices and vectors, right? EV is a diagonal matrix, P pi is a transition matrix, eta is just a scalar parameter, lambda is a scalar parameter. You can just generate a bunch of random matrices and then create this matrix A, and then use some linear algebra package which will give you the eigenvalues, and then you can just check whether their real values are negative or positive, right? Okay, that's something I can do. So I did it, and very quickly I learned that this is not right. And this was, yeah, that was a bad day. Because this was like months of work that I'd done. Like, it's not, you don't just come up with this, right? That there's a bunch of other things you have to show, that things are bounded, and they asymptotically track a bunch of things. Sorry, one second. And so there was a lot of things that I had to show it. This wasn't the only thing I was doing, right? And so I'd done all of that work. This was the only thing left. And I was like, yeah, it's like, this is the tabular case, by the way, right? Tabular off policy case. Well, this should be simple. And I could not do it for a long time, and then I just proved that it cannot be done. Right? So this was, yeah, like I was saying, it wasn't a great day. Yeah, you had a question.
Are you saying you can't just plug in any random matrices and just try to see if it's correlates? You have to correspond to an actual MDP, right?
I mean,
Like a Markov chain, you have to work.
I mean, as long as I maintain certain properties about those random matrices, I can say that, oh, for some random MDP that I don't know, like I can't visualize it, but there exists some MDP for which this would be the transition matrix. This could be a stationary distribution for some behavioral policy, and for some lambda and eta doesn't work. Like it, and you don't even have to come up with like very obscure example. It just very quickly doesn't work, right? Yeah. Anyway, so the point being that this algorithm can diverge, right? And okay, but after a few days, the sun rose again. Like, okay, failure is a part of science. Roshan.
I was just wondering, so you said that if the matrix is Hurwitz, then the algorithm must converge. But does it also mean that if it's not Hurwitz, it must diverge?
So intuitively, yes. What that means is you have some eigenvalue. Like in my case, I saw that the eigenvalues were positive, right? So if some eigenvalue is positive, that matrix, when it keeps getting multiplied with itself, that can lead to a blow up, right? And so, yeah, in my case, so if you have eigenvalues which turn out to be 0, then you might say, okay, maybe it doesn't diverge, but maybe it still doesn't converge. But in my case, they were just positive, right? I found many
But like it also matters about like the direction of eigenvectors, right? Like what if there was like B had no component in that direction, right?
Right.
But I'm not sure. I'm just like wondering whether the converse is that if it's not Hurwitz, it must diverge.
I mean, we should talk more because maybe then this works, right? Maybe it doesn't necessarily mean it not being Hurwitz that it won't work absolutely. Maybe there are some conditions under which it can work, and we can work it out. That would be great.
And there is other like thing is that like you're talking about this particular algorithm, right?
Correct.
But potentially there could be a small modification of the algorithm that makes it.
Exactly. So okay, so we started with one-step algorithm which we knew which had strong convergence proofs. This was the on-policy version of it. We created the off-policy version of it, and that apparently does not work. Now, after a while, I came up with this small modification, which is now that you have another trace parameter for the average reward estimate, and it is also updated in a very, very similar way. And it is essentially just a trace of 1, right? You're just adding ones and decaying those ones by lambda and with some importance amplification. But in the on-policy case, this is just a trace of 1. It will saturate to 1 over 1 minus lambda, and it's basically just a scaling factor for your eta. But in the off-policy case, it is doing something different. And then let's call this algorithm 2. And one thing that you can show about this algorithm is that at every point of time, your average reward estimate is a function of your value estimates, right? Like, let's say they all started from 0, then you can show that this property always holds if you're using this set of outputs. And then So this is like one form of your this thing that if this is your estimate, there should be a hat here, and you just combine them linearly according to some vector g, and then scale it with some eta, then this is your corresponding A matrix after a bunch of derivations. And if these things are true, that if your eta is greater than 0, and g is a non-negative vector with at least one positive element, which is a fancy way of saying it's like greater than or equal to 0, but at least one term is greater than 0, then it's Hurwitz, right? Which is great. And then, but yeah, like more technically, you will say that for any lambda, there exists some value of eta such that this matrix is Hurwitz. And it uses like the Perron-Frobenius theorem for irreducible non-negative matrices. Things I had to do, right? And then, okay, I'm really proud of this. This is, so there were two parts, right? One, you show that something is Hurwitz, and then you have to show the other thing that things are bounded and asymptotically track something. And there is this guy, Volker, who among, working on standing on the shoulders of other people who are doing similar things, has written this textbook which has like these modular theorems with which you can prove many things because they are very general theorems, right? But the thing that they are so general that you can't read them, right? Like it's like you can read it, it's English and math, but it's like reading some other, like, if I had to read Spanish written in English, I could read what those words are, but they don't mean anything. So the book is full of these things because they're general, but if you dive deep, you can make sense of them, and then this is the version that makes sense to me for the algorithm that I have, right? And this took a lot of time to come up with. Anyway, that was just a XKCD cartoon to show that this is all of our research. This is all the deep RL's new fancy stuff. Maybe this is TD, and this is the theory that Volker has come up with, right? Or like in general, like the ordinary differential equation approach and like some other theory. You take this out, everything collapses. Anyway, amazing work that these people done. Very underrated, and I had taken all of these things for granted before I dove into all of these things. But I have a lot more respect for theory. Okay, we don't have much time. Okay, so let me just tell you this. If we don't get through all of this, the point is just, this is something that I can do, right? Like, this is just to show you that I can write code which is bug-free, and because there are strong guarantees about what things should converge to, right? If you follow all the assumptions and such. So that just means you can write code which follows that thing, and if your code is bug-free, it will do exactly what you expected it to do, right? Question?
You replace the XZT with someone to make sure it converges, but it's not the only thing matters to converge. It matters to that you converge to what. And by changing that, you are changing what are you converging to. How do you ensure that we are going to the good place again?
Yeah, so I changed. Okay, sorry. I have to repeat the question for the online audience. The question was, there was perhaps a non-trivial change in the updates. Now you also have to show that the convergence point is still the one that was desirable, right? Or perhaps, of course, it can be true that you convert somewhere else, and you can show that, and then you can show how far that point is from the more desirable point or something, right? But in this case, in this tabular case, the fixed point is still the same, which is you follow an arbitrary behavior policy under some conditions. If you do these updates, you will convert exactly to the average reward of the target policy R phi and the value function for that policy, even if you made these changes to the updates, right? You can have multiple different algorithms, each converging to the same fixed points. And so this is an algorithm which does not change the fixed.
It's provable.
Yes, like that I have shown. Yeah, I should have a screenshot of the pyramid itself.
So
Yes.
you said it converges to the right point. Does it converge as quickly to the right point? And also asymptotia is a long distance.
Yeah, so now that's a very good question, right? So theory involves many things. One is maybe one thing is just to say, okay, for an algorithm, what is the fixed point? Like if you initialize the algorithm here, would it stay there or would it diverge? Right? Like that's the least that you can sort of say about your algorithm. Something more you can say is, oh, if I start from anywhere, I will end up at that point, right? So that's the convergence analysis, which is what you talked about. Ras is talking about something more, which is, okay, you told me that things converge. How fast does it converge? Like, is it super slow? Like, do I have to wait for infinite time for it to converge? So that is called finite time analysis, right? But yeah, I have not done it for these set of algorithms, but
That's next week, right?
well, I'm done with my PhD. I encourage someone of you to try to work out the finite time analysis. Right, but yeah, that needs to be done, and that can sort of say that, okay, how fast is convergence? Right now, we maybe don't have something to compare to because this would be the first multi-step average reward prediction algorithm. But you can always compare it to something that we know from before, like, oh, how fast did the discounted multi-step algorithm converge to, right? Did I see a hand? Yeah, Roshan.
So not to pile on too much, but like one thing slightly concerns me is that you said that there is parameter, and for if you make that parameter sufficiently large, then it can over. And I forget what the parameter was called.
It was sufficiently small, but yeah, same reference. Yeah.
Yeah, so is there a way of figuring out how small you need to set that parameter for the actual problem? It converge?
Okay, so the question is, in one of the conditions that I said A was Hermits if eta is sufficiently small. And the question is, can we know upfront for a given problem what?
Or not even upfront, but even like by looking at the data, can you figure out how to set the parameter?
Right. Yeah. So the question is now looking at the data, or maybe upfront, can you set the eta in a way that it will converge, right? So generally, I don't know how, but I think it can be done, right? It's sort of like saying that you have these step sizes, which you know that for most algorithms they have to be small enough. Like they have to start big, but they have to be small enough that they average out a lot of noise, but they also have to go to zero over time so that you're not making any updates, right? And so you can always conservatively set a very small step size and then wait for a long time for things to converge, and they will. But you could set it large, and if you think things are going too big, you sort of scale it down. So that brings us into the regime of like step size adaptation techniques, which I haven't analyzed as part of this algorithm, but there's a bunch of literature that does that, and yeah, these things can be put together. And I'm optimistic that.
So I guess we'll talk about this later after we're done, but I guess the problem here is that setting eta slightly big doesn't just mean that you convert slower, it means you diverge.
Right.
So that's
Yeah, so
I can talk about it here.
Yeah, sure. Yeah, maybe just start more conservatively. And but yeah, the thing is like these are the like next steps, yes, but then there is like now in the experiments you will see that there are some other conditions that according to theory, if you have things within this thing, it will surely work. But it's not that anything outside of that will never work at all, right? It's like, depending on what the noise that you see in your data and all that, things might still work. And like, for all of these problems that I'm going to show you, there is like a lambda max for which there is guaranteed convergence, right? But if I set it to something larger than that, a lot of times there is still convergence, right? And then sometimes, things do diverge as they could. And so, yeah, so empirically you can fudge things a little more and things might work out, but yeah, rigorously speaking, there is probably a narrower range for lambdas or etas. Okay, now I really don't have time for this, so I'll just say, some domain, random walk, you have some target policy, bunch of behavioral policies. And then you have learning curves in which, on x-axis you have some time, on y-axis you have an error metric of how far you are from the desired equilibrium, right? And so this should go down over time. And so first of all, I'll show you these things for algorithm 1, which was the on-policy case. So we are looking at the on-policy learning curves, and they look something like this, right? So this is for, all of them are for eta equal to 0.03. So for lambda equal to 0, there is some rate of learning. For lambda equal to 0.6, 0.7, it's slightly faster in the beginning, but maybe there is a little more noise or variance over time. For 0.95, again, even faster, but then, you are making too noisy of it. Okay, so maybe quick intuition of why about lambda. So remember the trajectory that we saw earlier, and then we saw, there is some fading set of updates that you're making. Now, it's good that you're making updates further in time, like in past, but things would be noisy. Maybe you accidentally see a reward that was noisy, and now you made a bunch of updates, right? And now you'll have to undo all of them over time. And so, just increasing lambda arbitrarily doesn't work. And that is what you can clearly see here, right? That in this case, for 0.999, there's a lot of noise, and then it takes a lot of time to converge. Okay, so yeah, asymptotically they all do, and some intermediate value of lambda works best in terms of like this trade-off that you want to learn quickly and also not have too much noise over time. And this is for one value of lambda, eta, but like for many other choices of eta, the trends look quite similar. Sensitivity plots. This means now how sensitive is the algorithm to the different step sizes you are setting, right? The ones that I showed you are the best step sizes, which led to the fastest learning for a particular lambda and eta. Now we want to see if I change the step size on aggregate, how low, right? And so this looks like this, that for, let's say, lambda 0.7, if your step size is too small for a eta of 0.03, across time, if you average your errors throughout time, like the area under the curve, it's pretty high. For a step size of 0.4, it's pretty good. But then if your step size is too much, yeah, it goes. So, you see these U-shaped curves, and this is all nice and as expected. Now, algorithm 2 is the off-policy algorithm, but you can also run it on policy, right? No one is preventing you from doing that. And if you do that, then, it looks pretty much the same, right? There's obviously some material differences in the two, but, squint your eyes, they more or less look the same. Okay, but the off-policy case is the harder case, right? And so now all of these are for algorithm 2, and now we'll have plots for different problems, right? So one problem will be with some behavioral policy, the other problem with some another one, and so on. So now these are 3 from left to right. The extent of off-policiness is increasing, and I've shown you lambda equal to 0 and the largest lambda for which things worked, right? That I tested and things worked. Right, and so for the on-policy case, this was like what we saw here, right? That 0.99 works, but it's very slow, and then some values in between. But then, as the extent of off-policiness increases, now 0.99 doesn't work at all, so it's not shown here. But 0.95 works. It's noisy, but it works. And then the usual trends with 0 and the intermediate ones. And it's even more off-policy. Now 0.95 also doesn't work, so now 0.9 is the largest value that works. And usual things, but we can also put this together that say that for a particular value of lambda, if you change the problem, how do things change? So this is for lambda 0.6, and the different curves are for the different problems, right? This is the on-policy problem, more off-policy, right? And so convergence is slower and slower, but it will eventually get there, the theory says so. I didn't run it for that long. I mean, I'm not showing it for that one. I did run it for like 100,000 times, and everything goes close to 0. All right, we're done. Yes.
Great. All this work seems to assume that there's one best policy, or there's 2 best policies. I go this way or that way.
Yes.
Does it oscillate? Does it choose one? Does it
So that's a good question. Russ is asking, what happens when, is it possible there could be multiple optimal policies, or perhaps he's alluding to what could be multiple equilibrium points.
Yep.
Right, and that's why there's some switching that goes. So in this case, the convergence that we are seeking is to the average reward of that policy and the values for that policy. If two policies have, it's like the same particle goal. If this goes in 10 steps, this also goes in 10 steps, then their average reward is the same. So this R pi 1 and R pi 2 are the same.
Yes.
So your algorithm will converge to some one of those, like in terms of the values that it converges to, R of x and V of x, that will be the same thing. Now if there is a difference in the pi 1 and pi 2, perhaps there is some switch, right? So there is, depending on what your exploration could be, or like what your step size could be, there could be some switches between the exact policies that you end up learning, but that can go to zero over time. Like you will have less and less of that switching over time.
So eventually it'll go to exactly one of the policies.
Yes.
Good to know.
Gotcha.
So, I really like your presentation, the different equation for it is very nice. So I just had like one concern, which is with the use of importance rates
Right.
in log policy. And I don't know a lot about this topic, but a few years ago I was looking at like sequential importance rating. And one of the problems that you have, like people talk about how sequential importance rating, the variance was different.
Right.
But like actually the reason the variance goes to infinity I found is that actually almost surely the importance range goes to zero in the long run, which means that basically in the long run you're not doing any updates, right? Like that's the way that convergence happens, is that in the long run you don't do any updates, right? And I was thinking, like surely, like when you talked about going from the sample base case to the ODE, you have to sort of control the noise, right? Like, and part of that is the noise in the importance rates.
Right.
In the algorithm, and so I was curious how you control that.
Yeah. So one thing, so for example, in the update of the traces, it's like rho times some lambda z plus something, right? Now let's say one of your rows is zero. Eventually there will be one. So the trace at that time is zero. You don't make any updates. Now let's say at the next time step there is some non-zero row, and you're in some state features x. So your update for the trace will be rho times lambda times 0 plus the feature value, right?
But once the row becomes zero, it can never become non-zero again, right? Because it's a multiplicative update.
No, but so if we were just accumulating all the rows, so there is an algorithm in which you can just multiply all the importance sampling ratios up to the current time and use that in your update. This is like the incremental version where you're looking at the per decision this thing, and so the per decision thing, even if it was zero before sometime, if at this time it's non-zero, we'll make a non-zero. But maybe I can answer another thing there, which is, the rows could be quite large, right, at some points as well, which also contributes to the variance. And so you do have to set some conditions saying that your maximum importance sampling ratio times the trace parameter should not exceed something, right? So the simplest thing to say is should not exceed 1, so there will be no explosion. But then that restricts the set of behavioral policies that you can use, which is, I think, not an unreasonable trade-off, given that I can't expect to learn about driving when I'm coding, right? Like they are two completely different things. So the thing that I'm trying to learn, I should be doing some things which are more or less aligned with it. And so even if it does cut down on the choices of the behavioral policies, I think that makes sense.
Yes, so I guess the concern, so I also came to the similar conclusions. So I guess the concern that I had is that the variance measures like how off policies are.
Right.
But the problem is that you need to set this parameter, which sort of squishes the variance of this important thing. And
You mean lambda.
yeah, I don't remember what
Right.
you call the parameter, but yeah, that's one.
Hmm.
And I think the problem I ran into was that the cost that you pay for being even a little bit off policy is like exponentially large in how off policy you are. So you kind of end up with these algorithms where on policy they work fine, but if you're even a little bit off policy, like it looks like it's converging, but the convergence rate is like increasing or decreasing exponentially. So like, yeah, it kind of, the analysis makes it look like it might be a non-policy algorithm. But actually, it's really a non-policy algorithm and it just totally goes up like when it gets even slightly off. That's not inherent in the problem. Like that's not because you're not getting enough data. It's just because of the use of important weights.
Yeah, so you're correct. So Rotten is saying that when there is enough differences between the target and the behavior policies, your trace parameters, they will have so much variance that convergence can be arbitrarily very slow, right? And so you do see something like that here too, right? That as the problem becomes more off policy, the important sampling ratios that word become smaller and smaller. So like the logical conclusion of this argument is that if your things are too off policy, you should not use traces. Just set lambda to 0, use your one-step method.
Or use some totally different algorithm scheme that does not use important things.
Right. Yeah. There are some like that. I guess I'm not super familiar with them, and like some of them involve, let's say, like estimating the ratio of the state distribution, which feels even harder. But yeah, maybe there is something there. I don't know enough about that.
And I think this is an open problem, so
Yeah.
it was a good point too.
Oh yeah. I mean, I made very sure that I boxed myself into something that is even possible, right? Like, for example, this is off policy tabular. The linear case is like a PhD dissertation on itself.
Oh, yeah, that's pretty hard.
Yeah, so this is very deliberately chosen to box in inside them. Okay, I think we are beyond time, so I'm happy to stick around for questions.